Okay, so yeah, let's start. Yeah, unfortunately, these days, so my talk will be about the Baryon asymmetry of the universe, and this subject is related to Andrei Sakharov, and unfortunately, in these days, I think it's I have to mention that. So Sakharov, he was one of the developers of atomic bomb, in fact, of nuclear bomb, but he got a Nobel Peace Prize because he was working on disarmament and so on, supporting disarmament very strongly. Apart from that, there will be for our talk, it will be very important that he worked on Baryon asymmetry of the universe. I will mention this in a few moments. But I think cooperation between all nations is very important to avoid events like what happens now, the war in Ukraine. And we scientists, I think we can be at the forefront of this cooperation. At least I hope so. For example, there is an open letter of Russian scientists against the war, and there are like 8,000 people signed that, and this could be dangerous for them, for those who are in Russia. But yeah, I hope this war will end as soon as possible, and we scientists should collaborate across the whole world. Okay, that was not the scientific part, but let's go to the outline of the talk. So I will start briefly discussing the standard model, and then I will describe why the Baryon asymmetry is actually a problem within the standard model. I will introduce famous Sakharov conditions. Then we will see the mechanisms which can solve the problems of the standard model, neutrino masses and Baryon asymmetry, and then I will present more technical stuff about so-called low-scale leptogenesis. This is a mechanism which can have phenomenological consequences. Like we can literally discover new particles, perhaps, if we are very lucky. Okay, this is the list of the references on which this talk is based. I will. So the first four are more theoretical about cosmology and the leptogenesis, and this three are about experimental searches. So I will be happy to share the PDF if you want. So all clickable links are here. Okay, so let's start with the standard model. So we all know it. Well, it's a very well studied theory which is based on the on the gauge group SU3 times SU2 times U1. We have matter particles here, quarks, leptons, and neutrinos. We have interactions, gluons, photons, and so on, and then the famous Higgs boson, which has been discovered already 10 years ago, actually. And according to Scientific American, the development of the standard model, both theoretical and experimental, lead to 55 Nobel Prizes, Nobel winners, like 55 people. Because yeah, there are not so many years, not 55 prizes, but 55 people got Nobel Prizes for their work on the standard model. And this theory explains everything, almost everything what we know about the universe at the time scales greater than when the universe was older than 1 second. We don't have direct evidence of anything before that moment. And let me mention one technical thing about the model is in this way, how it is displayed here. You see that neutrinos are only left-handed, so the diagram is not completely symmetric in this part, and this leads to conservation of numbers, just classically conserved numbers. The Baryon number, which basically makes protons stable, and then lepton numbers. There are 3 individual lepton numbers for each fermionic generation, and they are conserved. In in this description of the standard model. We will talk about this later. Okay, but is this the final theory? Well, hopefully for us, for those who work on particle physics and cosmology, the answer is no. The first evidence comes from Neutrino. Here you see super K. It's a huge cave filled with water with photomultipliers, and this has been used along with other experiments to discover the neutrino oscillations. So basically, in the sun, you produce neutrinos of one flavor, electroneutrinos, but then what you observe here is not only electroneutrinos. It has been observed that neutrinos, they oscillate. So basically you produce an electroneutrino, it travels through space, and then you produce electroneutrino, it travels through space, and then you observe, for example, a muon neutrino. This directly violates the conservation of lepton number. So the diagram on the previous slide cannot be fully correct because the lepton number is violated. Here, I showed this graph just to show that the evidence of neutrino oscillation is very, very reliable. There are many experiments, and this is the collaboration which just fits the data from different experiments. So this is a very reliable thing. Then comes cosmology. So this is this pie chart from Planck, and it shows the composition of the universe. So most of it is dark energy. We have no idea what it is. Could be just the lambda term in Einstein equations. Next, there's dark matter. We also have no idea what could it be. It spans like orders of magnitude. And finally, there's the ordinary matter: protons, neutrons, electrons, neutrino. But you see, I put question mark here as well. And the reason for that is if we take the standard model at the face value and the standard cosmology as we know it, there will be almost equal amounts of matter and antimatter, and we don't see that. So basically, we don't know the origin of matter. We know what's it made of, but we don't know where it comes from. So this is so-called Baryon asymmetry of the universe. Basically, there's no antimatter in the universe. There are different sorts of evidence for that. There's no, either would be, one can say, okay, there are some patches of matter and antimatter. Then there would be some annihilation signal from the interfaces between these patches, so we don't observe any type of signal like that. But more strong evidence comes from CMB, from cosmic microwave background. Again, you can measure the radiation using this Planck or WMAP satellites. Then you just do Fourier decomposition in spherical harmonics, and the height of these peaks it depends on the asymmetry between baryons and antibaryons. And fitting the theoretical curve with data, you can extract very precisely the asymmetry between baryons and antibaryons. This quantity is defined like number of baryons minus number of antibaryons. There are almost no antibaryons, so it's more or less equal to number of baryons over number of photons today. Because all of them, like the symmetric part has an annihilate. So at high temperatures, this quantity, we can define this quantity. Then over the course of the history of the universe, baryons and antibaryons annihilate. They produce you photons. So you have this number of baryons divided by number of photons, and this is a tiny number. So the asymmetry was really tiny, but all the matter which we observe, it comes from this asymmetry. Otherwise, there will be only photons. So we can fit that. Apart from CMB, we can also get fit from observing primordial elements like helium, lithium, and the error bars are larger because it's astrophysics, but still it agrees with cosmic microwave background. So we know this number pretty well. And Okay, what do we need to have this asymmetry? This question was asked first by Sakharov, and he formulated 3 criteria which need to be met to have a Baryon asymmetry of the universe. Those are famous Sakharov conditions. So first of all, Baryon number must be violated. Otherwise, if it is completely symmetric, if we start from a symmetric state, which we can expect very well if we believe inflation or whatever, then if there's no Baryon number violation, then there will be no Baryon number. Next, C and CP should be violated, and finally, deviation from thermal equilibrium must happen at some point. Otherwise, if you reach equilibrium, then even if you deviate, even if Baryon number is violated, it will be washed out, the symmetry. So, what about the standard model and Sakharov conditions? The Baryon number is indeed violated in the standard model, and this is due to so-called Sphaleron processes. So basically, this is non-perturbative solutions which interpolate between different Higgs vacuum with different particle numbers. At zero temperature, such solutions are described by instantons. It has been discovered by Toft, and their rate is extremely suppressed, basically like exponent to minus 100 or something like that. But at high temperature, you can jump over the barrier, and this process at very high temperatures becomes extremely efficient. This has been discovered by Kuzmin, Rubakov, and Shaposhnikov. So, okay, the Baryon number is violated in the standard model at very high temperatures. Now, what about C and CP violation? So we know that there is a CP violation counts in the standard model. However, if you compute how it works at high temperatures, basically, you see that this is not this number is tiny. So the CP violation in the quark sector of the standard model is very tiny, compared even to the small Baryon asymmetry which we're interested in. Okay, and next, there was a very detailed study of thermodynamics of the standard model, and it has been shown that if Higgs is heavier than 70 GeV, then there is no the phase transition between symmetric and broken phases of the Higgs is a continuous crossover. So there is no like strong first order phase transition, and there is no deviation from equilibrium. Okay, so that's the picture, and this is why we believe that the standard model should be extended. It cannot produce matter from which we are all made of. So let's take a look at this picture. It's from particle data group. It shows the course of the history of the universe. This is the earliest moments. You can see here energies, and this is basically also the temperatures at this period, and time. So this is inflation, something very early. We don't really understand what happened. Very high temperatures, close to Planckian, very early times. Then those are already energies accessible by accelerators. This is the nuclear synthesis. So this is the moment when we have the first evidence of Baryon asymmetry of the universe. And here you have the generation of CMB, when the universe becomes transparent, and we have a photograph basically of the universe at that period. And here the next evidence of BU is coming. BU stands for Baryon asymmetry of the universe. But in the standard model, at this temperatures, there is no B violation. So if the asymmetry comes from the sphalerons, which violate Baryon number, then it must be generated at very, very early moments. So if this mechanism is the correct one, then we'll have some evidence about the earliest moments of the universe, because we basically don't know anything about this period. Okay, so this was The introduction. So how we want to solve this puzzle? Basically, you need to make this table, which I showed, more symmetric. I will go to that in more details, and show how making this table more symmetric and nice can solve many problems on the standard model simultaneously. First, let's start from neutrino masses, and this is so-called seesaw mechanism. We know that neutrino masses are really tiny compared even to electron, to all particles of the standard model. The limits, the direct laboratory limit, this is cosmology, so it's basically below electron volt scale, and we know that electron itself is keV scale. Okay. How do we generate such tiny masses? Just a mathematical observation. Let's take this matrix and compute its eigenvalues, and let's suppose that small m is small and large m is large, just parametrically. Then one eigenvalue is close to large m, and another eigenvalue is equal to m squared over m. So it's parametrically smaller than small m. This can be realized in the standard model. So we take the Lagrangian of the standard model and add right-handed neutrinos, which are singlets with respect to all gauge interactions. We add them, and this is lepton doublet, this is Higgs, this is the right-handed neutrino, and this interaction term F is the matrix of complex. Give this small m in the formula before. But these particles are the only gauge singlets, and these right-handed neutrinos are the only particles which can have the Majorana mass term. And QFT tells us if the symmetry does not that we have to write down all terms which do not violate any symmetries. So this Majorana mass term should be written. And you can think about it that we have to make an experiment to fit what is m and what f. So this Majorana mass term gives us capital M here, and this is the way how we realize the seesaw mechanism. Just a number of relations which we'll use later. So if you have this seesaw, the left-handed neutrinos, the flavor states which interact with W and Z bosons and so on, they are composed of light mass eigenstates, like usually this is the PMNS matrix, plus heavy eigenstates with mixings theta alpha I. So every time you produce a neutrino, you have chances to produce a heavy neutrino, this right-handed neutrino, and the amplitude will be just suppressed by this theta. We will define combinations like if we sum over all flavors, we'll call this U square. This is the mixing angle of light and heavy neutrinos summed over generations. It will be quite useful for experimental plots. Okay. Why do we care about these right-handed neutrinos? Experimentalists actually call them heavy neutral leptons, or HNLs for short, and maybe I will also use the HNL. So HNL, heavy neutral lepton, is to some extent is a synonym of right-handed neutrino. More accurately, one has to speak about the mass eigenstates of this right-handed neutrinos. So again, suppose you have some meson. It could decay into a lepton and neutrino. And then every time it decays into neutrino, there are chances that it will decay to an HNL. And there were a lot of searches. The reason why I show this plot is just to show that it is very busy. The field lines are what has been already excluded by different experiments, and these lines show sensitivity of some future experiments. And what is on the axis? The horizontal axis is the mass of the HNL, and the vertical axis is this mixing with neutrinos. The blue line, for example, is ship, which it's a planned experiment at CERN, which will be extremely sensitive to these guys in GV region. And below this line, you cannot realize neutrino masses. So basically, you have a lower bound, which just come from the requirement that you explain neutrino masses. Okay, if you have some questions about this introduction, maybe we can stop for a moment, because then I will go to leptogenesis. Yeah, there are no questions, but if you feel free to interrupt me anytime if you have any questions. Okay, so HNLs can generate neutrino masses. That's great, and this is already a strong motivation for experimental search for such particles, because this is perhaps the most minimalistic way to explain neutrino masses and oscillations. Okay, but that's not the whole story. So they can also be responsible for generation of the Baryon asymmetry. And the mechanism is known as leptogenesis. It was initially suggested by Fukuhita and Yanagida, like the next year after Kuzmin, Rubakov, and Shaposhnikov discovered sphalerons. And the idea is that you have these HNLs, very heavy in the case of Fukuhita and Yanagida, and they generate asymmetry in the lepton sector. But then sphalerons transfer this asymmetry to Baryon sector. So, and this process is essentially quantum, because you have decays of HNLs. F is the matrix of Yukawa coupling, which I showed before. And then you have loop corrections to this 3-level decay. And just see that loop corrections, they have not only F, but also F star, these particles Majorana. And then the asymmetry or between decays of HNLs to leptons and anti-leptons, it is so-called epsilon, it will be proportional to the imaginary part of this F dagger F. So if not for the quantum corrections with this extra Yukavas, this term alone will not generate any asymmetry, because this is the amplitude. If you take if you compute the lifetime, the decay width, this thing will be squared and that's it. But because of the interference of different diagrams, you have the result which is not vanishing. So the asymmetry in decays of these particles is not vanishing. Moreover, it has been shown that the mass of this HNLs should be really heavy, above 10 to 9 GeV. Otherwise, you cannot generate enough asymmetry in this decays. But 10 to 9 GeV is clearly very far from any experimental, direct experimental researches. But fortunately, that's not the whole story. And next, I will discuss low-scale leptogenesis, where by the scale, I mean the mass scale of these HNLs. Right?
Inar,
yes. Yes.
So in this diagrammatic expansion here, how much under control is perturbation theory? So are you sure that this stops at one loop, or there are corrections at?
It's yes, it's a very well controlled, because this F much Yukavas, they should be small. So you have a small parameter. So it's a weak theory with extra small parameter. So the expansion converges very rapidly. You don't need to go to higher loops and already.
Right. So this automatically also means that nothing can spoil the result of one loop, right? You don't need to worry about that. Okay. Yes. Okay. Fine. Yeah. Thanks.
Yes. Absolutely. Yeah. Okay. But then when this bound has been derived, it was assumed that the masses are hierarchical. Basically, you have 10 to 9, 10 to 10, 10 to 11 GeV. And this is an important assumption in this result. So, okay, let me switch gears a bit and introduce so-called new MSM, neutrino minimal standard model. It has been suggested by Asaka and Shaposhnikov in 2005. And in this model, again, you introduce this right-handed neutrinos, And then two of them with masses above 100 MeV, basically, in GeV scale. They are responsible for Baryon asymmetry of the universe and for generation of neutrino masses via seesaw. And the lightest guy is dark matter candidate. And for this guy to be a dark matter candidate, it should be really weakly coupled. Otherwise, it would decay already. The fact that it's very weakly coupled to the rest of the standard model means that effectively you can consider a theory with two HNLs. And that's what we'll do in this talk. We'll only consider two HNLs. And if the masses are close enough, they can be in GeV scale and generate the Baryon asymmetry of the universe and neutrino masses. In fact, this mass degeneracy even preferred theoretically because it allows for, I mean, there's an extra symmetry which protects this mass degeneracy. And the mechanism for N1 generation, there are different mechanisms. The same N2 and N3 can be responsible for dark matter generation. This is quite fine-tuned scenario, but also if you allow for different description of gravity, for example, Einstein-Cartan gravity, at very high temperatures, it can produce, it can produce this dark matter. And Einstein-Cartan gravity is a viable theory which has the same consequences as GR, apart from very, very early moments in the history of the universe. Okay, so generation of Baryon asymmetry of the universe in the new MSM. Initially, this was suggested by Akhmedov, Rubakov, and Smirnov. Then it was formulated in terms of Boltzmann equations by Saka and Shaposhnikov, and they found out that two HNLs is enough to generate Baryon asymmetry. And then there was a lot of work by different groups, by different people on this model, on this mechanism. So people in Japan, in Germany, in Spain, in Switzerland, in Brussels, then in Switzerland, now also in Denmark, working on this. Okay, so before I describe this part, very heavy so-called thermal leptogenesis with the lower bound on the masses. Then I just announced that it is possible for GeV scale. I didn't go into details yet. There was yet another suggestion by Apostolos, Pilaktis, and Underwood that in the TV scale you can also generate Baryon asymmetry of the universe at the so-called resonant leptogenesis. These two mechanisms work with two right-handed neutrinos. And what I show here is my own slide from 2019. And the reason why I show the old slide is that since then the picture completely changed. So we thought that there are different mechanisms, but now it is not the case. It's all described by one and the same mechanism. Okay, let's see. So the reason why we thought that there are different mechanisms is the following. So leptogenesis in the new MSM, also known leptogenesis via oscillations, it only works, at least one can naively think that it only works as long as HNLs are lighter than MW. If they become heavier, they can decay into MW. Decay width is very large. And the fact that they decay very rapidly means that there is no deviation from equilibrium. And this is one of the Sakharov's condition. So there was a natural upper bound for the mechanism around mass of W. Next, why we can think that resonant leptogenesis does not work at lower masses? Because again, you need deviation from equilibrium, and if HNL is lighter than 130 GeV, it starts to decay at lower temperatures. I mean, the deviation from equilibrium via decays happens at lower temperatures when the sphalerons are not active. So the lepton asymmetry is generated, but it does not transfer to the Baryon asymmetry. So there is an upper bound around 130 GV, lower bound for this. So it has been believed that there is a gap between two mechanisms and they are not related. So, but how can we check? Is there a gap or not? We have nothing to do but solve the equations. This is a system of so-called quantum kinetic equations, and the quantum part comes here. So this is the number densities of leptons and the chemical potentials, and rho is a matrix, density matrix for two heavy neutrinos. And the fact that you describe this with a density matrix assures that you account for coherent quantum effects like oscillations and so on. So this term describes oscillations. This is decays of HNLs and the interactions with leptons. So basically, you have a set of integral differential equations. Then you can make an assumption about the spectrum of these HNLs, the momentum distribution of these HNLs, and then the system, you have a system of 11 kinetic equations. It's first order ordinary differential equations, but it's a very stiff system. And the most tricky part here is perhaps this rates. They are temperature dependent. So basically the coefficients of these equations, they change with time. And calculating these rates is a separate theoretical challenge, because there are many processes, and like the early universe is a hot dense plasma with all particles in equilibrium at temperatures above 100 GV. The W and Z and so on, they are really in the plasma, and you have to account for that. So there has been significant progress since well, over the years. It has been realized that new processes which violate Fermion number due to Majorana mass term have to be accounted for. Then mostly Mika line and Jacopo Kilgieri, they did a lot to compute these rates. Also resumming some T-channel divergences. There's also so-called Landau-Pomerantchuk-Migdal effect, and if you decay into two decay products of these HNLs, they have large moment and fly more or less together. There could be multiple interactions between them, gauge interactions, and even though it's next to leading order and perturbation theory, these terms are enhanced, so have to be accounted for. Then you have to account for neutrality of plasma, because when you generate lepton asymmetry, it is redistributed in the plasma, and so on. So a lot of work has been done, and then finally we also calculated the rates at intermediate temperatures, which have not been done before, and that's our result. So basically, there is no gap in this plot. This is the mass of the HNLs. This is the mixing, and white region is where leptogenesis works. So you can say, okay, this is the region where resonant leptogenesis is more efficient. This is the region where leptogenesis via oscillations is more efficient. But basically, it's one and the same mechanism. It's just different regimes of the one and the same mechanism. So I can try to give some idea why it's different regimes by using these cartoons. So this is time now, and number density of HNL is divided by number density of photons. This is the equilibrium one. So the orange line, it is constant, and then when temperature drops below the mass, they start to decay very quickly, exponentially. And let's suppose that the blue line is the actual density. So you have two moments when deviation from equilibrium happens. First, before the actual density reach the equilibrium one. This is what we call freeze in. And second, when they decay slower than the equilibrium like line. So there's another deviation from equilibrium. And the only difference between so you generate lepton asymmetry in both parts, but it is important when this asymmetry is stop being converted to the Baryon asymmetry. Basically, if the Sphalerun processes stop here, then the asymmetry which is generated here is saved in the Baryon asymmetry, and whatever happens next doesn't matter. But if it is generated here, then it is washed out during equilibrium, then it generates again, and it is saved like in the Baryon asymmetry. And this is sort of resonant leptogenesis. Okay, and in this plot, yeah, it's quite busy, but what I want to show several things. First, this thing can be extended well beyond the graph axis up to 10 to 6 GV. Our equations are just correct, so we show that there's a scaling. So this allowed region extends here. Then we need to slightly modify the equations. This can be done, but we just didn't do that because, sorry, there are no experiments which will be sensitive here. But this can be done in theory. And then, yeah, here somewhere here you have thermal leptogenesis. So basically, it's one and the same mechanism everywhere. And the color shows the mass degeneracy of the HNLs. So it's basically mass splitting of the HNLs divided by the mass. And you can see it can be as large as 10% or very small. The white color here means larger, smaller than 1 part in a million, like very mass degenerate HNLs. And why this is important here? This is, again, future experiments like SHIP, high lume LHC, or FCC. They will be really able to probe the parameter space of the mechanism. And just one more plot from this is the recent snow mass white paper which we put, and also the case with free right-handed neutrinos has been studied, and the bounds are even wider. So the allowed parameter space there is even wider than in the 2 HNL case. Okay, so that's it for the leptogenesis part. I think I have still maybe 10 minutes, right, or 5-10 minutes, and I will discuss experimental searches. Well, not all of them, of course, but just some. So again, this is a very busy plot from physics beyond colliders at CERN. And there are many proposed experiments which will be looking for these HNLs. The most prominent one, the most expensive one, is of course FCC, Future Circular Collider. They plan to dig a 100-kilometer long tunnel under Lake Geneva and put a new machine there. First, it will be the EE machine, and then hadron machine. And this EE machine, it will be really Z factory, like 10 to 13 or 10 to 11 Z bosons, so it will be extremely sensitive also to HNLs. And another competitor is SHIP, which works at lower masses. I'm a member of SHIP collaboration, so I'm of course a bit biased, but just to explain what SHIP is, so it's a fixed target experiment. There's an accelerator at CERN called SPS. This is the booster before LHC. And it produces 400 GeV protons, a very intense beam. And the idea is that this beam of protons hits a fixed target, so it's a beam dump type experiment. In this target, you produce a lot of stuff, also a lot of mesons which have chance to decay into HNLs. And then you have shielding, like 50 meters, nearly 50 meters of shielding. Basically, all charged particles which you have produced, and also all interacting particles, they are stuck somewhere here. Muons are deflected by magnetized shielding and so on. So what passes further is just neutrinos and some new physics particles. Could be HNLs, could be dark photons, whatever. then you have a huge decay volume, which is basically an empty tank. It's not even empty, it's evacuated. So there's no interactions of neutrino, for example, inside. And in this huge empty volume, the new physics particles could be HNLs decay, and then there's a tracker, colorimeter, spectrometer, and so on. So if something decays within this tank into charged particles, the ship will see it. And it's almost zero background experiment. So there are no standard model processes. The experiment designed in such a way that there will be no standard model processes, no neutrino interactions, nothing. So no background. And okay, then if we have HNLs, Majorana right-handed neutrinos, at colliders, the smoking gun signature is same sign leptons, because these HNLs, they are Majorana particles, charge conjugated to itself, and you can have, for example, leptons of the same sign, L+, like muon of the same sign. This is, of course, violates the standard model symmetries, but so do neutrino oscillations. And this is the smoking gun signature, because there is no standard model background. And this is how LHC looks for that. This is the LHC search. But then you think, okay, there's no way we can check this Majorana nature of HNLs at ship, because the decay product, first lepton, you completely lose it in the target. However, it happens so that you can do that. We have because the meson which has been produced, I mean the HNL which has been produced in the decay of meson, it carries information about the lepton with which it has been produced, because you have, for example, D meson with zero spin decaying into a lepton and an HNL, and then the spin is conserved. So there will be some angular correlations between decay products of the HNL. And this angular, so basically, if you have a lepton number violating process, in the rest frame of HNL, you will see something like that. If you have lepton number conserving process, you will see something like that. Then you don't observe the HNL in the rest frame; it flies over the detector, but still you can see some difference. Of course, the life is more complicated because there are many production and decay channels and so on and so forth. So one has to do some proper Monte Carlo simulation. We did that. To track the spin correlations, we have written our own Monte Carlo in Julia language, and then we train the classifier on this data. So you can see by eye that lepton number violating and lepton number conserving decays are different. For example, in these coordinates, then we train the classifier, in our case, boosted decision tree, to discriminate between these events, and this is our result. The field region is what is already excluded. The blue curve is sensitivity of ship, and the black curve is the region above which, above this black curve, you will be able to discriminate Majorana and Dirac nature of the HNL. So imagine you found some heavy neutral lepton at ship, and then you ask yourself, is this have we really found a particle which is responsible for neutrino masses and for leptogenesis? And then if it shows this lepton number violating signature, if it is Majorana, you can say, okay, this is the Majorana particle, and this is indeed the HNL. So no other experiment like BibNav experiment can do this, I think. Moreover, if you're extremely lucky, you can even observe HNL oscillations. This is related to also to production of dark matter in the new MSM. But yeah, I don't have much time for that. And the last message is the following. So this heavy neutral leptons, the primary motivation to study them is because they can explain neutrino oscillation data. but it happens that mixing angles or the mixings of HNLs with neutrino, not all of them are allowed if you want to explain neutrino data. And the field regions here are the regions where, like this is mixing with electron, with mu, and with tau. We normalize them to the total mixing, so they all have to sum in one. So that's why I can plot them in this triangle plot. And the colored region is what allowed. However, the experiments usually consider single mixing, like only electron mixes with HNL or only muon mixes with HNL. This would correspond to the corners of this diagram. You can see that corners are basically excluded by the neutrino data. And then, but this is what experimentalists used to do. Now Atlas considers after this work. Now Atlas considers, for example, points in these colored regions, but not before. So let's take some exclusion limit by Atlas. This is a black curve here, and one can show that this is under the assumption of the single mixing. And one can show if we account for neutrino data, what is excluded for sure is only this gray region. And in principle, the heavy neutral leptons can hide somewhere here. Different lines correspond to different points here. So for example, oops, sorry. So we think that this is excluded, but it is not the case, because the mixing was not a single flavor mixing, but some more complicated combination. So there are some chances even to find them perhaps in already excluded regions. Okay, this is the same story about lighter masses. I guess I can skip it, and I'm coming to my summary. So yeah, leptogenesis is relation between neutrino physics and very early universe. That would be the evidence of the earliest moment in the universe. And then the Baryon asymmetry can be produced because of right-hand neutrinos and the masses range from MeV to GAT scale. The experimental searches are complementary to each other. For example, LHC, SHIP, and FCC, they will be studying different regions of this parameter space. And what is also important is that some reinterpretation of experiments is required, because we could have missed these HNLs in the data because of the assumption of single mixing. Okay, that's it. Unfortunately, I cannot hear you. I think I see that room B07 is not muted, but I cannot hear anything. Is it on my side or?
Wait.
Yes, now I hear. Still nothing. Maybe using the laptop or.
Yeah, so we're going to use the laptop. Thank you, Inar, for your good talk. We have some time for questions. So if anyone has one, please go ahead. Although we have some technical difficulties with the microphone. So we will
maybe
not
you can
be able to
repeat
hear
if I
you,
cannot
Inar,
hear.
until the end of the question. Is that okay?
Yes, sure.
Okay. So anyone has a question? Okay, so there is a question. I'm going to with the laptop.
Or maybe you can just repeat.
Hi, Inar, thanks for your talk. It was very nice. I wonder if these recent measurements of the W mass in Fermilab have any implications for leptogenesis. Could you comment on that?
Yes. So
wait a second. Wait a second.
Can you hear me now? Okay, yeah, I see. I see thumbs up. Okay, so in fact, they not directly to leptogenesis, but they Fermilab compares. If we forget about the tension between Fermilab and Atlas, there is a tension between W mass described. Sorry, determined from the muon decay. And the W mass measured by Fermilab, the CDF. So if you basically if you introduce new channels to muon decay, then it will, I think it will effectively enlarge G and reduce G and enlarge MW, and then this reduces the tension between MW from muon and the CDF measurement. There were, I think, already 2 papers on that mentioning HNLs, because the HNLs can do this. They basically can the corrections coming, loop corrections to muon decay involving HNLs, they move the W mass into in the correct direction. However, this introduces tension with Kabiba angle anomaly, because you also have this Kabiba angle anomaly, and if you want to reduce both tensions simultaneously, then the HNLs cannot do the job. Moreover, I think the region where HNLs can solve the CDF tension is already excluded experimentally. I have not checked yet. So if I go, let me see. If I go to this plot, for example, the region where HNLs can solve the tension is somewhere with very large mixing angles. So somewhere here, somewhere along this line, they can do the job, but part of this region is already excluded. And also, if I remember correctly, I did an estimate, and I think this violates tree-level unitarity. Basically, decay width is larger than mass for such HNLs. So to me, it's questionable. This solution doesn't look very appealing. On the other hand, the CDF measurement is in tension with Atlas, so it's also a question. Yeah, I think that's all what I can comment on this issue.
Inar, can you hear me?
Yes.
Okay, I think we solved this. So any more questions? Okay.
I have one
Okay,
question.
Go ahead.
So Inar, can you hear me well?
Yes.
That was not the question. You mentioned when you were discussing baryogenesis, you mentioned that you have this dark matter candidate. I don't remember well whether this candidate is coupled to the other sector, but I wonder whether by knowing the abundance of dark matter that implies some constraints on the details of baryogenesis, or
so yeah, this is the dark matter candidate. So the new MSM is really minimal model. You don't need anything except right-handed neutrinos. So you only extend standard model by right-handed neutrinos. And then this N1 will be the dark matter candidate. However, let me see if I have a slide. Unfortunately, I don't have a plot right away. So then there are following bounds. First of all, it should be stable enough. But then if it is too light, then there are some bounds coming from Lyman alpha and structure formations, if it is too light. But then you have a trouble to have it stable and not decay into not producing some X-ray lines. The mixing should be really tiny, and then thermal production of such dark matter doesn't work. So what works is so-called Schiff-Fuller mechanism. So basically for that you need a large lepton asymmetry around 10 to minus 4 lepton asymmetry to entropy density, which will boost production of this dark matter candidate. And this surprisingly can also be achieved along with the baryogenesis in the same model in the new MSM. So these two guys, they first produce baryon asymmetry. This baryon asymmetry freezes because of tolerance, but then they keep oscillating and producing very large lepton asymmetry. This large lepton asymmetry boosts dark matter production. However, for this mechanism to work, they have to be really mass degenerate. And let me show, I think I have a slide. Yes. So green region here is delta M mass splitting, and this is some parameter. So mass splitting should be 10 to minus 7 electron volt. This is close to neutrino mass splitting. This is something. This is unnatural. So many people are not happy about that. However, there are some other mechanisms. It could be produced during inflation. Higgs inflation and Einstein Gardner gravity will generate the right amount of this dark matter. But it is there is yet another story about 7 keV dark matter, this 3.5 keV line. It has been, there are some claims that it has been observed. Then there are some claims that it has not been observed, but the final decision could have been made by the satellite Hitomi, but unfortunately Hitomi on the orbit, the satellite turned itself in pieces. It started to rotate instead of compensating rotation and destroyed itself. So there is a successor of the satellite, XRISM. I think it should have been launched this year, but COVID, of course, delayed everything. So it should be launched in next few years, and then we will know the final answer. Because there are some people who believe that they see the signal of this decaying 7 keV dark matter.
Thank you.
Yeah, thank you.
Okay, so I think we're good on time. So let's thank again Inar.
Yeah, thank you very much for having me.
Well, thank you everyone for coming today, and hope to see you again in the next seminar. Bye, everyone.
Yeah, let me see. Yeah, bye. Thank you very much.
Bye, Inar. Thank you for your talk.
Bye.